Right, so then without further ado, I can just move on to the topic that I wanted to discuss today. I'm really thrilled to be on the conference that is all about clocks and time and thermodynamics. You will not see any thermodynamics here, but I really have to be interested in the relation between the two theories. So maybe if the time allows, I can just say a few words at the end, or maybe even post some things for the discussion later today. Because where I'm coming from to the topic of clocks is perhaps a little different, although I'm aware that many of you would have similar perspective.
Do you mind? Yeah, how do I do full screen share?
No, it's okay now. I think I just needed to revive it. It's a theorist approach. I touched a few buttons and now it works, so I don't touch anything there. All right, so I'd like to say a few words about where I'm coming from, because well, there are old friends at the audience, but also new friends or people I haven't met. So I'm based currently at the University of Stockholm, right here, but I just moved there in February from Brisbane, Australia. I'm there thanks to the Valentine Foundation, one of the few organizations that are keen to fund fundamental research. And so I'm working on exactly the topics I'll be discussing today. So the insights we can gain about interplay of quantum mechanics and general relativity by using composite quantum particles. And in particular, for example, I focus on why, when we talk about composite quantum particles in the context of relativity, we are directly led to the notion of the clock. I'll explain you where this perspective is coming from. So the other topics I'm interested in my research. So today I'll talk about the interplay of quantum mechanics and GR. I'm also interested in causal order. That's of course something that also becomes a really interesting notion once you have of quantum mechanics and GR. But it's perhaps a bit more on the fundamental aspect than possible things we could test there in the lab. Have some interesting testing alternative models that are proposed out there that could modify quantum mechanics or GR, given that it's difficult to combine them or difficult to get an agreement about what exactly would that even mean to combine them. Yeah, and also some fundamental topics about quantum space-time superposition that we're exploring in collaboration with Rockman from Waterloo. Today we'll talk about quantum and gravity, and since this conference there will be a lot of fundamental discussions about what exactly constitutes the clock, and I will be coming with a very simple model. I thought to include a little bit of a perspective why or where from is this approach coming. And this comes from the fact that when we talk about fundamental unanswered questions in physics, of course, quantum gravity comes to mind. So when I talk to people who have quantum mechanics and gravity, they ask me if I do string theory or other topics, and of course it's nothing of the two. And the reason not to directly jump to answer that question is that if you would like to find a new theory, find a theory that describes quantum gravity, essentially that would be about finding a theory that describes phenomena when gravitational degrees of freedom are quantum. And for that, of course, like for any other theory, we need to understand what is the phenomenology and essentially have experiments. So when we ask ourselves, okay, what do we know from experiments about how quantum mechanics and gravity work together, then essentially the experiments we have where we have the quantum phenomenon and gravity plays a role are all in the regime where we can fully explain the gravity visible in the experiment in terms of the Newtonian description, so non-relativistic space-time and just the potential. So one class of such experiments are interference experiments. Here we have a picture of an actual interferometer used in the first such test in the 70s with neutrons. So in this experiment, neutrons move into the position of different paths above Earth, and because of potential, there is energy difference, there is the phase acquired, and we can measure this. Something that may not be so much appreciated, but it's only in 2017 that we had the first experiment that was, so until 2017, it was not even that this was just the Newtonian limit. It was a Newtonian limit and homogeneous gravity. Now in 2017, there was a first experiment where this phase measured in such an interferometer that was done with a different technique with atoms. The first experiment when it was necessary to introduce a correction to the homogeneous potential. So essentially, it was for the first time that quantum mechanics had seen that the gravitational potential on Earth is not just equivalent to constant acceleration. And so this really is striking when we compare this to the aspiration of finding quantum theory of gravity. So we are far away experimentally from understanding, from being able to observe phenomena that happen in the future. Another class of experiments that probe Newtonian gravity and quantum mechanics that I like to mention, I think they are very fun and elegant, are experiments where essentially, again, neutrons are put in a potential well that is created due to gravitational potential and some, essentially, a marble table on which you drop the neutrons. So you have a classic first-year quantum mechanics problem. You have a potential well, it's just not square, but it's a triangular one. If you literally go to Lambda Ellipsis, I guarantee that you'll find the solution there. I found it there myself. And you can solve for the eigenstates in such a well. You find every functions and quantize not just energies, but also you see these are the wave functions of the particle in the trap. So these are spatial wave functions, and this is the height, which means that if you have the particle in the ground state of such a well, it will not be lying at the bottom, the same as for harmonic potential, it will be somewhere above. And so there were experiments done in the group of Magdalena Zych and also carried out now in Vienna, in Hartmut Agale group, where such states were measured and even radio oscillations using some other states were observed. So these are really the two classes of experiments we had. And we would like to move forward. So we would like to make experiments where we need, in order to describe the outcomes of the experiment, to have the degrees of freedom that are subject to the experiment that require both quantum mechanics and relativity. And of course, there is a fundamental framework that describes such a regime. If you go really ab ovo, you will have quantum theory in curved space-time. So if you study that, you'll see there are various predictions for new phenomena, so it's not that we are at the loss of new predictions, but simply because of how the framework is formulated, the natural way for this framework to deliver predictions is in a high energy regime. So there will be effects like Hawking radiation or Unruh radiation, various other effects that essentially live in the regime of high energy. So if we think of high precision tabletop experiments, it's difficult to envision we can directly again jump to probe some fundamental effects of quantum physics in space. So something else is needed. And so somewhere where relativity and quantum mechanics comes together, and many of you of course would be well familiar with that, is when we make measurements of time. So measurements of time are the most precise in terms of methodology that we can make, experimental we can make. And typically, in such systems, the heart of the workings of the system, the hardware would be atoms and lasers, so it's all the systems for which we need the quantum description. And so if we think of atoms that make from the heart of the atomic clock, there were experiments that tested time dilation between different atomic clocks. And of course, what was going on there, that we had atoms and their internal states, they were providing the tick mechanism for the clock. However, and by positioning these two different setups in laboratories, so there was an experiment in the Weinland room where they have two setups, independent atomic clock setups with all the lasers and everything, and they could shift the position of a table on which one of the setups was sitting relative to the other table, and they could measure redshift between the clocks that were separated by some, well, plus 33 or minus 17 centimeters I think they didn't have very continuous control of the height of the table, just these two heights were recorded. Maybe you have a reference. Or they could use the trapping potential to essentially move the atoms that were forming the heart of one of the clocks and test the prediction of Doppler shift or special relativistic time dilation between the clocks that were moving some order 10 meters per second. So this is sort of like the everyday walking pace. So if we think of such high differences or some speeds, and ask them all, do you think these are relativistic regimes? Typically, we would say no, but actually, essentially, what's going on here is that we ask, are we in the regime that we should call relativistic or not? The question is how precise our measurements are. So this shows us that we can make very precise experiments where relativistic effects can matter on these small time scales, at distance or energy scales. So in these experiments, of course, the internal states of the clocks we need to describe quantum mechanically. However, these time dilation effects here, they are captured essentially classically because the position of the clocks or where these atoms are sitting effectively can be given a classical description. And so that's a good anchor for what we want to talk next. So given the high precision of experiments that we can achieve with clocks, and that they are based on essentially composite particles, so atoms seen as something that has internal structure. The goal is then to look at composite particles subject to relativistic effects and consider what are the low energy, what are the new effects in the low energy regime where we need to describe quantum mechanically of the internal state that provide the ticking of the time, but also the external degrees of freedom that define essentially what the word line is or what the time dilation should be. So the framework for this, you can start from, there could be many starting points to describe such a system. You could take a number of interacting particles. If they are insufficiently small space-time volume and external fields are not changing widely on the scale of the system, then you can find a regime where effectively such a system can be described by its center of mass or center of energy, whether in that case coordinate and relative coordinates. And that's essentially what would be the model for the rest of the talk. So here when I talk about the composite particle, essentially it would be something like an atom that is composed of at least a proton and electron, and we can find a regime where this system, even in when we add relativistic correction, can be described as some center of mass, trajectory, and internal states relative. And it's of course quite convenient for atomic systems because the spectrum of an atomic system, the internal energy is well known. I mean, these are exactly the spectral atoms that are more theoretically well understood and measured. So this is just to highlight that you can approach these things from various theoretical perspectives and more or less converge on the same low energy limit. So I'll now just jump directly to how these systems look when we look at the low energy limit. From this it will be easier also to see the implementation. So this is essentially a Hamiltonian. When we massage the previous theories, you looked exactly to this form where we have some center of mass coordinate for a composite system. And so the momentum here is conjugate to the center of mass position. And then internal energy, so this could be all the energies of the electrons bound to your atom. They are all packaged here in this term that I like to call n hat. Now why I like to call it n hat is because essentially this is the energy of your composite system in the rest frame. So by definition, this is what forms what the meaning of this term in relativity is the energy in the rest frame. Now for elementary particles, we consider this is some scalar quantity mass. But for any system that has internal structure, so has some degrees of freedom relative to the center of mass, this is the energy in the rest frame. So again, for something like an atom, this will be Hamiltonian. This is the zeroth component of the metric, and of course it's still there because we aspire to describe these systems in the presence of the gravitational. Now it's interesting to look how this theory is described when we use the Lagrangian. So you can just do the Lagrange transform and find the Lagrangian for the system. And it just has this simple form where the tau dot is essentially the speed of the proper time relative to your coordinate time. That part is the rest frame Lagrangian. That I don't have it highlighted. The rest frame Lagrangian, which is essentially just what is the Lagrangian corresponding to your. Now this has a nice form from the point of view of trying of being some interest in describing time, because we see that essentially we recover exactly the same structure we have for elementary particles with the Lagrangian, is just proportional to proper time. It's just that here we have some dynamical Lagrangian that just captures the dynamical thing. But now this is not extremely convenient because if you want to again apply it to something like an atomic system, considering the Lagrangian of the discrete internal levels, it's not very practical. So this looks like there is some trade-off between having this form where we understand very well both the quantum mechanics of phase space of the center of mass and internal energy, and here we have this formal object. And then one can do something else. So this is just to highlight that this is possible, but in the rest of my talk I'll actually look at the low energy Hamiltonian, just to give you a heads up. But I think it's interesting to realize that as a theorist, you are allowed to do a partial Lagrange transform and just define the center of mass in terms of the configuration space, tau, and leave the internal energy in terms of the phase space. Sorry, I sneaked. So this is essentially the same as M-squared. Okay, copied from two different plots, so here it shows. So such a functional where some degrees of freedom are described in phase space and some in the configuration space is known as Gaussian. You probably might have seen it in your classical mechanics where you want to integrate out a constant of motion. So it's a very popular technique when you have system under constraint. And so you have some conserved quantities in the Lagrangian. You can swap them to the Hamiltonian and just use their conserved momenta. They are not dynamical, and you reduce the number of degrees of freedom you need to track. But of course, you are allowed to do it also in other scenarios. And in this case, it gives you this interesting structure where you have internal structure described in terms of Hamiltonian. So then again, you can capitalize on the fact that the kind of systems you are interested in here, we know everything about the internal spectrum, while the trajectory of this object wouldn't capture in terms of path integrals. So in that sense, I view composite quantum particles. Well, classical is actually applies to classical systems, of course, as well. In this sense that I see them as the model of an ideal clock in relativity. So of course, it doesn't have all the other things we need to count time, but it has the structure that, from the point of view of the Einstein model of an ideal clock and how we define events, it has the required elements. Namely, it has some internal states that can change, and it has some space-time trajectory. Well, here it's quantized, of course, it's not going to have a classical trajectory, but it has the center of mass that can follow trajectories, and that are, of course, necessary to capture if you want to talk about possible effects of relativity. So you need to be able to capture also quantum mechanically the position degrees. And so this is this fact about composite particles in relativity, that their dynamics take this form, is what makes them a good model for a theorist to play with the notion of time at the interface of quantum and relativity. Okay, so I'll maybe move on. I would like to now look at the low energy limit of this Hamiltonian Hamiltonian, and this is simply because for today I want to focus on some predictions from this framework that could be interesting for testing in the lab, and that would go beyond the limit of Newtonian non-relativistic effects in quantum systems. So now if we do the typical low energy expansion for this square root, so now I didn't really write down the metric, so this metric will be 1 plus the Newtonian potential, which is this function here. We'll get this form of the Hamiltonian. Now you have the small p here, which essentially means that this is the non-relativistic version of the momentum. It just means that the relativistic corrections that will be in this term because of the metric are neglected. That this order is essentially the regime where the center of mass is effectively non-relativistic. It looks like we went all the way and too far. We lost all the relativistic effects that could possibly be there. But this is not quite true, and this is exactly because we have a composite particle. Now the M hat, as I was repeating countless times by now, it's the internal energy of the system. So it includes dynamics. And I like to divide it into, say, ground state energy, and then I call the ground state energy little m, and all the spectrum above by this H in that stands for the internal dynamics. Essentially, this part of the rest energy is the relevant one that drives the internal evolution. The ground state, of course, is irrelevant. Now, if you include this split, I mean, this split is, of course, somewhat arbitrary. And if somebody asks me, okay, how do you split the atomic energy? Do you start with like chromodynamics? Like, what is the ground state? So this is theory dependent. But this is, I mean, this is not detrimental to this approach because this really asks what can be observed in a particular scenario. So if I apply some microwave laser fields to an atom, I can pretty well capture the ground state as the electronic ground state and excited state as some, or even optically separated. So this split can be meaningfully done once it's clear what the context of the application. We talked about nuclear processes, and of course I have to make this split somewhere at the level of how the nucleus is bound with. So if we now include this split and we look the form of the Hamiltonian, then we see a bit more clearly that we have some relativistic corrections. And so effectively they can be seen as corrections that come because of the mass energy equivalence. Essentially because of the internal energy being part of the mass. Relativistically, there's just one mass parameter. When we do this expansion, we end up with something that non-relativistically we like to call kinetic mass and the gravitational mass. But they are all one and the same parameter relativistically. And therefore, if we have the rest energy relativistically that includes internal dynamics, this is true for the low energy function. And so these terms essentially come from this theorem. So we get relativistic corrections that essentially come from the fact that we have this internal energy that couples to the kinetic and the potential. Now they have very simple interpretation. Yeah, I mean, I'm suppressing higher order effects, and this is simply because we talk here. So this is not your typical 1 over c squared count. There are some 1 over c squared terms that are suppressed, and this is simply because we are interested in the regime where center of mass is very, very low at very low energies, like the ground state of some harmonic trap, while the internal dynamics, let's say, is some optically separated entities. And so this will be the interesting regime where the energy, so the correction of this type where you have internal Hamiltonian coupled to the kinetic term, they are larger than the term where you have just pure center of mass correction. Now, the interpretation of these terms is very simple. So this is the gravitational time dilation or redshift of internal dynamics, and this is the special relativistic calculation. So you can see that for some semi-classical or classical limit of this Hamiltonian. The P on M just gives you velocity, so you get the lowest order approximation to the Lorentz factor. 1 minus v squared over c squared over 2. So this just how time dilation, that is of course inherent part of the relativistic theory, shows up in the Hamiltonian formulation of this composite couple. So in experiments that I talked about before with atomic clocks in the lab, so the actual big setups that comprise many moving pieces, its internal states do require quantum description, and this is part of how we understand the Rabi oscillations and interaction of these atoms with the laser light. But the positions of the atoms in the traps are essentially treated classically. So the natural regime of application of this theory is where we can leave this restriction and consider scenarios where the dynamics, the center of mass, the positions of the clock require quantum description. So that's what this kind of line of research started with. So I want to briefly show you the first really application of this to find some interesting scenario where this would matter. And so this is essentially a version of this time dilation experiment that I talked about. It's just instead of a pair of optical clock setups, you consider a single atomic particle. So this is a thought experiment that hopefully soon you might somewhere. I'll talk about it in a minute. So this would stand for an atom, for example, and now like in the time dilation experiments, it can we have two possible word lines. So with pairs of clocks, you put one at the lower height, the other higher height, or you have a pair of twins that move on different trajectories in space-time, and they start at the same age, and as they meet again, they would age differently, and that's what we know as a twin paradox. So now you can run the same idea, but with a single clock, and you put it into the position of traveling along two different word lines. And of course, along each of these different word lines, you'll have now different. So the idea is to have word lines with different proper times. The internal states would then evolve by a different amount of time, and the coupling that I just shown is exactly what dynamically give rise to different dynamics of the internal state depending on what the center of mass is doing. So get here that the internal state of the clock would evolve by a different proper time depending which word line is moving. And of course you end up then with a system where the path is entangled to the internal state. And so apart from relative phase that will be there like in those experiments with neutrons, you'll also have some correlation with the internal state that will depend on the amount of proper time difference relative to the period of the clock. So if you put a few numbers, in particular consider just this very simplistic static height difference between the paths, and the two-level clock with some frequency omega, you get as a prediction the blue line here that shows the beating between different frequencies, and of course one of these frequencies associated with the clock and the other with the phase. Or you can view it as a manifestation of the which way information versus interference visibility complementarity. So the internal states, they reveal which path the clock has taken, depending what's the difference in the proper time to the period of the clock. So this point in the plot is exactly where the proper time difference between the trajectories is equal to the half the period of the clock. You can interpret it in different ways. And the prediction is essentially that instead of just an interference pattern, ideal interference pattern that you will get in the non-relativistic theory, or in the relativistic theory, but when you use an elementary particle with no internal degrees of freedom, so this will be this black dash line. in relativistic theory, when you have a particle that acts as a clock, and for this you need to prepare your system in a superposition of different energy levels, you'll get this blue line, and yeah, this overlay here is the So to be clear, the goal of showing this is to highlight that in this kind of experiment, we have a chance to disprove the description of the experiment in terms of quantum mechanics and non-relativistic gravitational potential that would just give you a phase difference. And again, the interpretation of this is that in the Newtonian physics, or if you look at the fully Newtonian limit of the Hamiltonian, there are no coupling terms, there is global time, and so no matter which trajectory the clock is taking, the internal state always evolves by the same amount of time. So this experiment could disprove this description and will be this modulation of the visibility arising because of the interplay between the proper time and the path of the clock. So would be an effect for which you need both quantum mechanics, I mean, to get the interference, to explain the interference in the first place, and in new relativity. So this is the sense in which this approach can lead to experiments that can move a step further in our ability to test quantum mechanics. So in terms of number, I mean, this is challenging, of course. If you put the Earth's gravity and internal levels with the optical frequency, you need for this height difference. Actually, the figure of merit is the space-time area of the interferometer, so for how long your clock stays in the interferometer and how big is the path separation. You need for this something like 10 meters times second. Well, this is hard. There are efforts on the way to realize such an experiment, and maybe I'll just mention the group of Ravel in Hanover. They have by now finished already a building where they are building 10-meter size atomic fountain, where one of the goals of the apparatus is to realize this kind of experiment. Right, since I'm not going very fast, I'll maybe move on. So I highlighted how such particles, at least to the eye of a theorist, naturally present themselves as ideal clocks, but they can also be seen as ideal test masses. I mean, the fact that the Hamiltonian actually has the form of something where you can put a hat on M, and the M understood, of course, is the total mass energy, suggests interesting insights into the meaning and test of equivalence in quantum mechanics. When coupled to external fields, they can be, or they connect to a very well-loved model of particle detectors in quantum field theory. So here there is a chance to consider this kind of particle detectors that also are quantized themselves in terms of their trajectories and where they interact with the field can be quantized, so this can be some interesting insight. And of course, also from this approach, if you have a clock, you can also have a thermometer, so you can couple them to some thermal baths and consider them as thermometers, so you can have a description of a thermometer whose position in the bath can also be quantized, and this can be interesting. So these were all the incarnations of this framework, and in the remaining time for my talk, I wanted to mention two more specific applications of the framework that I hope will be of interest. So yeah, the first one is again going back to atomic clocks, but this time a little bit more in detail. So this will be now looking at these composite particles when they are trapped, because we would like to really think of them as the atoms that are used in the setup, and see what changes in the description of such a particle and what relevance it might have for those particular applications. So we'll be considering some additional potential. There are some additional references for different trapping potentials with different contexts for similar questions. It's a relevant references for this topic for now. So again, we are looking at already at the low energy limit, and this is again justified by the fact that the ideal operation for these atomic clocks are really pulling down the atoms to the mass. So the energies of the center of mass are much smaller, in fact, in thermal energy. So we can So another simplification or approximation we'll be doing is considering homogeneous gravitational field. So that essentially is because we will be parameterizing the Hamiltonian not in terms of the time of a faraway observer, but in terms of the laboratory time of some nearby clock in sits on the gravitational field of Earth, and approximating the potential with just theory's favorite simplest harmonic trap. So typically when one considers a particle with internal states harmonically trapped, we usually like to think that we can just write down the spectrum and everything is already known because we have the spectrum of a harmonic oscillator and then we have internal states and it will be just a tensor product with the basis. But things are not quite like this if we include these relativistic corrections that come here through the mass energy. So one way to see this is essentially if we try to keep going and just quantize and just diagonalize this Hamiltonian with the standard approach, introducing normal mode operators, rotation and inflation operators. We can follow the usual recipe. We see that the mass still enters here. I mean that while it looks maybe a bit unusual, it's in fact a very it's very clear what's going on. We have so here this one on m is just an inverse of the mass operator, which is positive spectrum. So it's an operator that has eigenvalues 1 on n and the same eigenbasis as n. So for each eigenstate of the mass, we just have a harmonic oscillator, but with a different n. And so that's of course relevant both for defining the mode, normal modes, and the frequency, and also the effective minimum coordinate for where around which coordinate you're crossing the trap. So that's effectively when you have a pendulum under additional force that the minimum shifts, and it depends on the mass. In this case, because this external force here is mass. So this would be this directly gives rise to the Hamiltonian in the more familiar form. So again, for each mass eigenstate, we have some frequency and we have the normal mode operators, and I wrote them like here to now highlight how the normal mode operators for the different internal energies connect. So you'll see that the center of mass description, the center of mass states depend on the internal energy. And then again, it's quite intuitive for anyone that studied the harmonic oscillator. Your wave functions do depend on them. I mean, if you have smaller, larger mass, they will be more or less localized. And that's exactly what you get. The modes for the different internal energies, which means for different masses effectively, are related by squeezing. And of course, displacement. And this is because we include the external, there's the external gravitational potential. So it's all captured in here. And the full Hamiltonian is then, here we have for each mass energy eigenstate, we have the corresponding energy eigenstate, it's just the sum. So it has a very simple structure in that sense. And what we find, just to summarize the main important aspects here, is the spectrum is still of a product form, but it's not a product of bases, so the basis states are correlated. So for each internal energy, we have some number states. The center of mass frequency depends on the internal state. That's another important aspect. And yeah, of course, the modes themselves. So this is more the picture that we are getting. Now for the specific context of atomic clocks, it's worth to look at the energy difference between two eigenstates of this Hamiltonian. That they look like this. To So to highlight, this would be just the energy gap between the ground state and some internal state, and then we have a bunch of terms here. And the fact that there are a bunch of terms that come to you with internal Hamiltonian in context of trapped atoms is very well understood. I mean, there are interactions. And but the relativistic effects are typically captured holistically. So for example, this term here that one can derive even from the simple model is known as a time dilation shift in atomic clocks, and it's it appears essentially to the experimenter as even if the clock is in the ground state, as a particle, it's not really sitting still. There is some residual energy, and if you express this energy in terms of just your kinetic energy associated with some velocity, and you compute the Doppler shift associated with that velocity, you get a shift of the frequency. So effectively, when you trap an atom from the point of view of this semi-classical treatment, you have the particle that moves a little bit in a trap. And for a thermal state, there is of course some distribution of these velocities, and it gives rise to some spread in the frequency of the clock. And so that's something that one can derive from this approach. And of course, there is an additional shift here that comes. So this effectively comes in because of this shift in the position due to the gravitational field. And maybe perhaps just to people really involved in this research, it's interesting to realize there is some minimum. I mean, one can minimize this and find the parameters where this shift has the minimum value, but it's not so fundamental. So if we look what this predicts for the kind of experiments that are being carried out when one talks about moving atom on the clock. So one typically looks at some Rabi oscillation. So we prepare the atom ideally ground state of the trap and internal state, and then one uses lasers to prepare superposition. The evolves for some time, then it's measured again. So a typical interferometric experiment. But now the fact that we have these correlations between the center of mass state and internal energy states means that if I prepared my system in the ground state of the trap when the internal state was also in the ground state, and now I excite internal state, the center of mass, together with this internal state, they are not an eigenstate of the Hamiltonian. So there will be correlations that are developed, and this leads to the pattern that looks like this blue line, rather than the ideal Rabi oscillation pattern that would be the green line. So the green line essentially you can interpret as in the absence of relativistic corrections, and the blue with the relativistic corrections, here just coming from special relativistic effects, and here including the gravitation. So, these are the kind of predictions one can make essentially for what would we see for a trapped particle subject to something like a Rabi oscillation. So this can also be used, of course, as possible means to test again the interplay of quantum mechanics and GR by looking for these type of effects. Not necessarily with an atom in superposition of some meter-separated path, but by high-precision measurements of an atom in the trap. And I think the interesting thing from the point of view of the conceptual aspect here is that essentially we are talking about the possibility to measure time dilation effects that are just because of the inherent finite spread of the wave function of the atom in the trap. So not between separated atoms in different setups, but really kind of relativity at the scale of the individual molecular functions. And of course, maybe just going back to this minimum predictions, you see the scale of these effects. Essentially, you need to be able to make experiments with a fractional. If you turn it into the typical figures of merit in atomic clocks, so fractional frequency precision on the order 10 to minus 22, 23, which is very high, but actually we do have tangible plans to go to such precision. So that's another avenue one to test this interplay. And maybe I'll just put it up with particular other interesting aspect is that coming from fundamental physics, this is interesting in order to test the interplay of the two theories, but from the point of view of high precision timekeeping, this is something that I believe will have to be taken into account in the future. So, as this evolves, I guess. I wanted to talk also about another aspect of these particles, and maybe I'll just highlight the topic, but I'll not go through. Actually, it's not that much content, but I think it makes no sense to really drop much more onto your head. So just very briefly, when we have these composite particles that we like to use as flux, ideally we would like that the center of mass with all the internal states moves on some trajectory and measures the proper time of trajectory. That would be. Now people looked at propagation of these composite particles, and what they found essentially, as the particle moves, the internal energies spread and delocalize. So there are particular papers that have looked at this. And so the question is this something unavoidable? If so, then the whole premise of using these particles, this ideal clocks that just move and measure proper time, is out the window. But if not, then the question is what's going on. And so I'd just like to highlight that, again, the assumption was that when describing such particles, we can take the center of mass, define some state, and then take internal energy states and prepare them in any state you want. And we can run with the usual interpretation. So essentially, taking a semi-classical state for the clock was understood as necessarily meaning we can take a Gaussian state for the center of mass, and then consider internal states in some superposition that then will peak and evolve as the clock is moving. But if you look closer at this means that we take some state that minimizes the Heisenberg uncertainty in phase space. Now we want to talk about semi-classical trajectory for a clock, and trajectories are defined in configuration space. So we want to talk about states that minimize the position and velocity uncertainty. And of course, we find that if you're in the non-relativistic physics, essentially just mass parameter, we define velocity and momentum, there is no difference. It's not like this in relativity. And even in this low energy regime, just the statement of the uncertainty, even in the low energy regime, when we look at the velocity operator, that can be just computed as the derivative of your position operator, we obtain something like this, and the low energy limit, this just becomes P on n, but if you want to use this particle as a clock to test some relativistic effects, we have to necessarily keep all the internal energy states here. If not, we are back again to the Newtonian. And if we do it, so yeah, if we keep this correction, then essentially we need to address the question: what are the states that minimize this other uncertainty, not the phase-based uncertainty? And there's all the machinery to do it. And again, in the low energy, you get a state that is a Gaussian, but again, a Gaussian that are center of mass Gaussian states that are correlated with the internal energy. And again, it can be easily understood through the mass energy equivalence. The peak momentum will have to be mass dependent if you want to have the velocity the same for the different mass components. The widths also have to be correlated. That perhaps doesn't have such an easy intuitive interpretation. At least I didn't find one, but that's So I'll just skip ahead and I'll just put up some cartoon. And so that's essentially what's going on. If you compare the evolution of a Gaussian state times some internal energy superposition over 4 different masses to these position velocity minimum uncertainty state, you'll find that there is some difference in how the internal states evolve, but there is no necessary delocalization. So here is some other interesting insight you can gain, and I'll just put up my conclusions. And if there's any remaining minutes, do we still have a couple?
Yeah, 10 minutes.
Okay, perfect.
So we have some time for questions.
Yeah, so I'll just put up my summary.
I guess we have time for questions.
I have a couple of yes/no questions about the modified Bragg relationship. Would you mind going back to this?
Yeah.
So, okay.
No, sorry. You can start asking.
Yeah, sure. So there's this, just to understand the graph, this is taking the Hamiltonian that you had before back, and then now adding a semi-classical oscillating field term, and then solving. I mean, in order to get these Rabi oscillations, you need an interaction with the field, right?
Yes. So no, you need an interaction with the field. So these are just predictions based on the following premise. We have some Hamiltonian of the particle and includes this relativistic correction. Now when we shine the laser pulse, the assumption is even with the relativistic corrections you can find, I mean this is just more how I think that's typically done. I mean it's not the right above like all the duration and the intensity, it's more there is some degree to which you need to really optimize for a given setup, and then you understand for what parameters you prepare equal superposition of the population in the grounded excited state. So the assumption behind this plot is we can prepare a superposition of the internal state equal superposition ground excited. The center of mass for these plots is really taken just as the ground state. I think one could take low temperature thermal state. Yeah, we have quite lengthy formulas in the paper. It's not very insightful, but essentially the assumption is then this is the starting point for the state, and then it's just the evolution captured during the dark time. So just the internal evolution of the center of mass and the internal states after the superposition was prepared.
So it's not this kind of driven Rabi problem. It's like a free evolution of the.
Yeah. So this is superposition, some amount of time of free evolution, and then the measurement taken into account.
Maybe I should see the floor for my second question.
At some point you displayed this term in the equation of motion where you have a coupling of the internal and the center of mass degrees of freedom. I think I've somewhere encountered this at some point where someone discussed whether this would generally make the clock, say, less precise, but I never really understood whether one can make a general statement whether somehow these correlations between internal and center of mass degrees of freedom, whether one can say that generally if those two degrees of freedoms are getting entangled, if you use this for a quantum system, for example, whether this would make the clock worse, or whether there's actually a way that one can use this as a resource to get a better clock.
Yeah, this is an interesting question. Of course, if you by clock understand just the internal states and consider that you will only prepare or want to manipulate those, then the fact that there are these inherent coupling terms with the center of mass, this is just what relativity gives, beyond any other couplings because of the actual setup and the fields you need to control the clock. In that sense, they will make it less precise, just simply because you will develop correlations that if you don't take into account, they leak out the, I mean, you can call it depending how you like information, or they leak out coherence from the internal states. But of course, it doesn't say that there is a fundamental limitation in the sense that it's still a system that has Hamiltonian with a spectrum, and if one will be able to manipulate both the center of mass and internal states, you can still consider running theoretically the same argument that we just prepare superposition of states of the Hamiltonian, but then you need to address these degrees of freedom together, which I guess technically is not as straightforward to say, well, we prepare a superposition of these correlated ground excited states for the atom in the center of mass. It's maybe not very clear. But this is just the practical.
Yeah.
I don't think that just the fact that there are these correlations means that this necessarily puts a fundamental limit. It gives the fundamental limit if all that we want to do is the same as we are doing before, and just addressing the internal states and sort of hoping for the best or trying to minimize the effects of these external states.
I think that sounds reasonable.
There's 3 more questions about kind of talk at the same time. Okay, will it take this for three questions.
Okay, so thanks for great talk. So would we consider that quantum mechanics in general relativity activities whom effect may offer? So is there a possibility of altering this kind of dynamics? Is there a possibility that whom effect may alter the dynamics of this composite particle system?
Definitely there will be additional terms if you consider that, yeah, it's some charged particle and interacts with electromagnetic fields beyond just the external fields of light. So you, for example, if you use this model and that is where a particle is coupled to a field, even if this field is in the ground state and the particle is moving, it effectively captures exactly the Unruh effect. Now, in terms of the practicalities, whether there's a chance to detect the Unruh effect with atomic clocks, I think some people have looked at it. It's always a question of precision, but in principle, if one wants to be more precise, one would need to add interaction terms with all the fields kind of that we have, and they will all contribute to the effects here. So, in principle, yes. I mean, there will be some counts or some there could be excitations just because of the atom being coupled to an electromagnetic field, even if it's in the vacuum, which for particular configurations will be interpreted as a
Cool. Yeah, thanks for that talk. I wanted to ask about, this could be just a stupid question, but spin and change statistics and whether that could be interesting in this context. For example, if you have a composite particle made of two fermions, that will eventually look like a boson if they're close together enough, whatever that means. Is there some way of seeing some interesting general relativistic effects in that context from the fact that the statistics changes somehow or on some scale?
Yeah, definitely. I mean, even just looking at the particles with a spin already gives in relativity some additional effect. I mean, spin doesn't transform as a scalar. So yeah, I mean, the general answer is yes. I didn't think of these composite bosons in terms of how the statistics and interplay with the localization and relativity, how they could affect it. It's not very interesting. But yeah. Yes.
Okay, last question.
In the last part of your talk, when you look at the time of flight and keeping the light packet together, is there a complementary route to that where they say you're in momentum space instead of configuration space? So if,
Yes.
yeah.
Yes, I think I actually even may have a picture. So yeah, if you do the Gaussian wave packets, they will spread in position. But for maybe I just actually I have a nice. Yes, I just go out of the. I was still maybe to go out.
Oh, yeah, the person stage maybe.
Okay, yeah.
Yeah.
It will be much quicker. I'll just put out this. So these are Wigner functions for the Gaussian and the minimum alternative state. For the Gaussian, it spreads in position but doesn't spread in momentum because here we look at the free particles, so the momentum would be invariant. And so, yeah, there is this interesting complementarity. Like minimum uncertainty state, they start already spreading momentum by definition. Yeah, that is the I think that covers everything.
Okay, let's thank Magdalena again.